Hey, if you're new to the channel, my name is Siddhant. I'm the host of Constructing Tomorrow podcast, where I cover topics related to construction and technology. I'm trying something different out today. I am visiting one of the buildings here at Georgia Tech, which is the most sustainable building here in Georgia. And in the world, it is ranked the 28th building to successfully complete the Living Building Challenge. So stay tuned for the entire tour of this building. Today we have Jimmy with us. Jimmy, you want to introduce yourself?
Jimmy Mitchell, 19 years with Skanska.
Yep. So today we are at Kendeda Building. It's a beautiful building, and we're going to show some of the cool sustainability features. But Jimmy, if you want to just give an overview of what the building is and what it's used for at Georgia Tech.
Sure. It was gifted by the Kendeda Fund. In terms of the program, we have a 180-person auditorium. This student commons area, we have 2 large classrooms, 4 class labs, a 16-person office space, and what kind of most importantly, it achieved the full certification of the Living Building Challenge. So it's a great example of a program that's needed on campus that achieves the full certification of the challenge.
So if you want to shed some light on what is Living Building Challenge.
So the Living Building Challenge is a rigorous certification that is both, things to do for sustainable elements and an advocacy tool. And the big concept is regenerative design and construction. So how our buildings can give back more than they take. Traditionally, the problem has been we build these wonderful buildings and there's unintended negative consequences. So Living Building Challenge projects, how can we have intended positive consequences?
Cool. So let's just take a walk around, and if you can show some cool sustainability features and teach something about it, I guess. Oh, I didn't walk this space when I came this morning.
This is one of my favorite reuse stories. I'm a Georgia Tech alum, and back in 2016, the Tech Tower, which was the first building on campus, went through renovation, and they added a fire stair and an elevator. And as a result, the original wood structure from the 1880s, those little bits had to come out for the new elevator and stair. And we saved, Georgia Tech saved those materials.
Oh, wow.
Yeah. And so these stair treads are 1880s heart pine joists that came out of the Tech Tower. Now, one thing that's really fun about this is we worked great with the design team, Nordic Sargent Miller Hall, to come up with fun ideas and then review the constructability, the reality of them actually happening. This was one that the original design was an amazing butcher block type stair that was a new product, but compared that new product to just sanding the wood joists from Tech Tower, this ended up being a $60,000 savings on our budget.
Wow.
So it's a great reuse example of how it can save money, under the right conditions. One thing that was really great they did architecturally is, as you can see how beautiful wood is when it's sanded, but we did not sand the underneath of it. And so on level 1, the monumental stairs underneath, you can still see what the original joists looked like when we pulled them out of the Tech Tower.
Apart from sanding, did you need any other treatment on the wood?
Yeah, so the wood had been treated, so everything in the building would be treated for longevity.
Okay.
One other thing that's really important about a Living Building Challenge is the materials Petal includes the red list. So the red list is 20 chemicals, class of chemicals that are known to have harmful effects like carcinogens. Some of them are obvious, like we don't use asbestos anymore. That's one of the 20. But others are less so, like lead, chromium-6, PVC. And so when we do have the finishes for the wood, the materials and the sealants can't be on that red list.
Got it.
So everything here does have a level of treatment on it, but it's not. It has a low amount of VOCs, volatile organic compounds, and then it doesn't have those red list chemicals. All right, so this is a good place to talk about the water Petal. We're in the basement, and on the other side of this concrete wall is a 50,000-gallon cistern. And the project is built and designed with a water treatment plant here in the basement. So rainwater gets collected on the roof, sent into the cistern, and then it gets treated to potable levels here. So water has a couple of nuances. Let's start with stormwater. When there's rain events, the water stays on site. So we have underground infiltration systems. It's basically recycled HDPE pipe wrapped in a geotextile. That's like an underground pool that when it rains, it allows a volume of water to go in there and then it infiltrates into the aquifer. Only in like rain events that are like a 50-year rain event or a 20-year rain event does that fill up, and then some of the water would then go into the stormwater system or the street or whatever. That basically it's designed as if there are woods here, and if there was a 50-year rain event, then there'd be runoff in the woods too, right?
Got it.
So then the potable water system we just described here, this then goes out into the building. So all the water in the building comes from rainwater. It is capable of doing that. And then finally the black water system. So when you go to the bathroom here, it's a foam flush composting system, and the leachate is separated out. That goes to the water treatment facility, and then the solids stay here in the composting bins, and eventually over time there'll be some compost that gets extracted from the process. So the whole water system acts, we use the water on the way to the aquifer. So it's as if we're not here, and this building recharges the aquifer like nature would have.
Talking wood.
So one of the other imperatives is embodied carbon. Lowering the embodied carbon, then if you, any of the carbon you emit through the process of building the building has to be offset. So one of the structure types that is favorable for this type of project is timber. Now our structure here is a combination structure. We have concrete, we have steel, and we have timber. Now, one thing, the combination of the queen post trusses with the steel rods and the timber was a smart way of using both structures. So without the steel rods and post truss there would be a whole lot more wood in this wood structure. So we tried to be smart about that. Using wood, but minimizing it intelligently with, the combination of steel mixed in. Believe it or not, that saved us a lot of money on the project, and it allowed us to lower the floor to ceiling heights as well. So this building would have been about 3 feet taller without that as well. So we want to maximize the wood in the project. You see the glue laminated columns and beams. Also the nail laminated timber panels are made out of wood. There's a lot of millwork and reuse items. We actually have fallen tree bar countertop here. That is, wood, the ramps, the stairs. And so you can see wood is just a really common and beautiful product. And you see it a lot in these types of projects. Okay, so one of the big factors is trying to reduce the amount of energy it takes to operate the building. So the primary way this building gets heated and cooled, especially in the extreme temperatures, is through radiant flooring. So we're currently standing on like miles of PEX tubing that's in the concrete. And so when it's really hot outside, chilled water runs through the tubing, and when it's really cold, hot water runs through the concrete to condition the space. Now, the other thing is that the deadband temperatures, so the temperatures when we want to condition the air, are pretty wide. It goes from like 68 degrees to 78 degrees. And so when it's on the upper end, let's say it's 95 degrees outside, if a ceiling fan is on and it's 78, you actually feel cool and really nice in here, but you also can still wear your shorts and flip-flops, right? And so we have 62 ceiling fans and 4 of these big fans. So here's 2 here in the atrium. So right now we have a pretty pleasant day, but on a summer day when it's in the 90s, they would be circulating in the air and keeping it nice at a low energy level. So ultimately, this EUI, energy use intensity, so the amount of energy it takes to operate the building per square foot, is really important. So let's say a standard building will have a number of like 80 or 90. This Kendeda building, its EUI is like a 15, 16, 18. So we're using a whole lot less energy to operate this building compared to a standard built.
So talking about energy, I guess I'm curious to know what are some different ways it produces energy. I read somewhere that it produces 200% of the energy that it consumes.
Right, it does. So the way the energy works here is it's net metering. So at night, we're consuming energy from the grid. Right now, we're generating energy, so we're sending energy to the grid. In the course of the full 12-month measurement period, we've been sending more than twice the electricity we're using. When it came to the design and construction of it, a lot of power generation considerations were taken, but ultimately having the one large solar system was the most cost-effective way to do it. And the other thing is that these solar panels, they generate electricity, they collect water, they shade the building on the west side, so they end up having a lot of benefits.
Did you run into any issues of needing specific number of solar panels and then you have to reconfigure the roof spacing? Yes.
So that was one of the most fun things about, say, the value engineering phase of the design. Yes, we had to stay in budget, but the discussion was centered around the 20 imperatives.
Okay.
So if we were like, okay, yeah, let's add an espresso machine in the coffee shop, you know, the coffee cart area. All right, well, how much electricity does that use? How many solar panels is that going to require? Does that mean we're going to expand the structure? You know, and all these consequences will come. And so the value engineering discussion was, how does it all fit together?
Got it. You can see the downtown from here.
Yeah. So I want to tell one of those stories about a design idea that had a lot of implications. So early on, very early on, we knew there'd be some green roof aspect, but this concept was actually a couple of the large classrooms would be above the auditorium. Well, based on skin to floor area ratios, we, as the team was discussing it, we realized we could create a walkout rooftop garden from this level, move those 2 classrooms over to the west side, and enough efficiency would be gained in that process that we would be making a 5,000 square foot rooftop garden, but actually saving a couple $100,000 on the budget. So it was an amazing value engineering idea. And from the imperatives, it's beautiful.
Yeah.
You see the urban agriculture. Here's blueberries, and the students plant other vegetables. We even have the honeybee project out here that generates food.
Oh, really?
Quite literally honey. So another great example of the benefit of this roof, you know, but there was a negative. This 5,000 square foot, formerly from the water engineer, was a water collection space, but now that it's an occupied roof, we're not collecting the rainwater from this area. So here, you can imagine, you know, this walkout green roof benefited 8 things in an amazing way, but it was negative on the water Petal, and we had to solve that problem separately. And we did.
Yeah.
But it's a great example of a design idea, you know, having...
You cannot meet all check boxes.
You can't make it perfect. You know, you got to. It's all got to eventually work together in a tight
cohesive manner. Yeah.
Yeah.
Do they often have classes in here, or is it just random?
Classes?
Yeah.
Oh yeah. I mean, there'll be 1,100 people who go through this building in a hot day, in like a fall or
Oh, I
spring
see the
day.
classrooms going on
Yeah.
right now.
No, they try to avoid those 8 a.m. classes, you know. So I mentioned the Kendeda Fund. Diana Blank, provided the funding for the Kendeda Fund, and she's a bird watcher. And this is not a part of the challenge, but this frit right here is to avoid bird collisions. And so Josh Gassman worked with the Audubon Society, and we try to maximize the places where to put this frit up and to reduce bird collisions. So it's a really fun thing that Diana Blank wanted, and we were able to pull off. And there certainly are fewer bird collisions here, and it's a great thing to do.
It's just like a film?
Yeah, so it's just film on one of this 3 panes of glass here, film on one of it, and it's a little bit of a bird ethics. This dot pattern probably avoids 96% of bird strikes, right? And so certainly there might be a way to cover the whole thing up and be 100%, but this was where we landed at. All right, so really the best reuse story is the nail laminated timber panels. So if you look up, these panels are really the big question on how do you span the decking? And we have NLT. It's a 2x6 nailed to a 2x4, repeated thousands of times. And we built these all on a table upside down. And structurally, the 2x6 sits on the beam, and the 2x4 is really just spacing the 2x6. So that allowed us to salvage the 2x4s. So we worked with a local nonprofit Lifecycle Building Center, and they collected from 3 different film sets. When they're done with the film set, they strike it, they tear it down, and they throw it away. We had them collect over 25,000 linear feet of the 2x4s, and we nailed them into the panels. And so we have 25,000 linear feet of formerly film set 2x4s in our decking and roofing structure. Not only that, when David Luffel, our senior superintendent, who was an amazing carpenter who put all that together, he needed carpenters to help him. We went to Georgia Works, a local workforce development nonprofit with the formerly incarcerated homeless men getting back into the workforce. David trained 6 of those men to help us make the 489 panels over the course of about 4 months. So it ended up being a workforce development program. One of the things is that this was kind of crazy, right? So when we went to get pricing to do these panels, we didn't really receive any qualified bids. One group out of Canada was $800,000 more expensive than when we penciled out doing it ourselves.
What was the reason for it being that expensive?
A couple of things. Reusing the wood. No one was willing to 100% guarantee we could do that. The other thing is the new wood had to be FSC certified, and there's supply chain constraint issues with that. And then this NLT process isn't common. So when you talk to the market at the time, they would have said, what about tongue and groove? And then at that time, they didn't even have the CLT options like we do today. But why not get CLT from Europe or something like that? So the design team wanted this look, this fluted NLT look, and we needed to pull it off. So I actually went to Home Depot one day with a couple of people from Skanska, Mikhail Gasly, and at the Grinnell warehouse on campus, nailed a 5-foot by 12-foot panel on the floor as a mock-up. And it took me 44 minutes to do it with a nail gun. And we used that as our labor rate to interpolate that across the whole building. And when we did that, labor and material came to $800,000 less than our qualified bid.
Oh, wow.
So the fact we self-performed it is what allowed us to incorporate that workforce program. And it was great because it, here again, it's one of those items that these panels really benefit a lot of the imperatives, including equity, because of the workforce training. All right, because that energy use intensity is so important, we risk when class gets out of the doors being held open for minutes. And that, believe it or not, would be a lot of energy lost, in particular with the humid air coming into the space. And so where we have these entrances, we have air curtains. And that air curtain is a great way to avoid the air mixing between the outside and the inside. Mm-hmm. And believe it or not, it's really important for energy.
Why do we have metal on this side and wood on the other side?
Yeah, that's just what it was. Mm. So this metal was out here too, and so it would have been a continuation of.
Oh, probably. Yeah, that makes sense.
Yeah, and the way this was is like, this is really still kind of an outdoor space in a way, in that vestibule. So we, I mean, it is indoors, but like this is double pane glass.
Yeah.
The rest of the glass is triple pane.
It is exterior from the top, so maybe they just.
Yeah, they wanted it to visually be seamless.
Yeah.
Between the metal panel on the exterior and then this side here, where over here, this part of the design was wood, and so we continued the wood on the inside of the vestibule. Yeah. Really pretty. This brick over here is a great facade, and it's a green leaf brick, which is all 100% recycled brick.
Okay.
And so you also get these muscadine vines here, which is a vertical urban ag surface. When you do the calculations of that, you can count the vertical and the horizontal areas. And that's another one of these calculations that it's determined by the floor area of the building and the limited disturbance of the site. And so this is really grown in well here for the first 10 feet or so.
I was just curious, what about the furnitures inside the building? Does that have to be also considered, or you can just buy anything?
No, the furniture was, I have to say, Lord Sargent took the lead on that. But it was strongly considered for all the red list and the sustainability requirements and the volatile organic compounds. And so big part of the process for LAS.
Got it.
So this is a fun thing. When we had that value engineering idea, using the case the structural engineer put together for the queen post truss inside with the wood structure, they then carried that through some other areas. And this articulated column is a king post column where it looks almost like a light sail here. And that is in kind of the spirit of that interior structure. So it's great because the design team really leaned in on some of these sustainability ideas and made them beautiful. And this articulated column is a great example of that. So one great tool is passive design. So how can we build something that can passively benefit the project, especially with heating and cooling? So the solar panels were offset to the west, and there's a lot of glazing on the west side, which is kind of a no-no because in the hot south, during the sunset is when it's the hottest outside, and now you're getting a lot of thermal heat from the sun into your building. So passively, these solar panels offset to the west really does shade the building and cool it until that sunset moment. Well, that's when these mature trees can help. So in the summertime, the foliage is full, it blocks that sunset sun from coming into the building. And in the wintertime, the deciduous trees, the leaves fall, and when you want some of that sun coming in, it's available. So it's just one good passive example of how we can use nature to our advantage.
Well, I think this was great, Jimmy. I really liked it, yeah.
Thanks. Anytime.